This video is about integrators. It corresponds to section 36.1 of Applied Analog Electronics. All right, let's take a look at the circuit. We have got an op-amp. And it is configured as a negative feedback op-amp with a resistor and a capacitor and the positive input is set to a reference voltage, generally in the middle between the power rails. Okay, we can figure out what this thing does by looking sort of at first principles. We know that because this is an op-amp in the negative feedback circuit, that the voltage here is going to be kept at Vref. All right, so let's take a look at the current that flows through this resistor. That current has got to be the same as the current that flows through the capacitor here, because there's no current through the input of an op-amp. All right, and again, we can use what we know about the components, resistors, and capacitors to get that I is V in minus Vref over R. And also I equals C times d Vref minus Vout dt. All right, we can equate these things and rearrange it a little bit. First of all, the derivative of Vref minus Vout with respect to time, well, Vref's a constant, so the derivative of that's just 0, and we're just going to get minus the derivative of Vout with respect to time is I over C is V in minus Vref over RC. And what that's saying is that if the input is larger than Vref, then we're going to get Vout on a downward slope, constant straight line downward slope. If Vn is less than Vref, then this is going to be negative over here, and we're going to get Vout constant upward slope. And what determines that slope is not just the size of the input, but also this RC time constant. So we've got voltage divided by time here. That's the correct units for slope for a voltage with respect to time. If you want to write this as an integral form, we can write this as Vout equals the negative integral of Vn minus Vref over Rc plus some initial constant value. And this is the formula that makes this thing called an integrator. Now, obviously, there's some little problems with this if you try and do this in the real world where you don't have perfect components. One is that Vout is limited to the voltage between the power rails, or whatever the output voltage range is for this particular op-amp. Once you get to the limits of the op-amp, you get clipping, and the thing stops having this nice derivative behavior. That's a serious limitation. That is what we have to make sure when we're using an integrator like this, that we've got some way of keeping Vout in a reasonable range. This arbitrary constant, the initial value, is something that we have to think about and worry about a little bit. The main use we're going to make of an integrator in this course is to make a triangle wave oscillator. And in that triangle wave oscillator, when we get to one end or the other, we will be switching which direction the integration is going. We'll be changing the input to get either a positive slope for an upward going ramp or a negative slope for a downward going ramp. And either way, we can make this thing work quite nicely and not have to run into trouble with hitting the limits of the op-amp. That's pretty much all we need to know about integrators for now.